In this video, we'll use InCA to set up a new manufacturing process model from scratch. We'll then run that analysis and plot the results. So we'll start by adding a new process involving overmolding of composite reinforcement. The process will be split into separate activities, so we'll need to add those activities one by one. Activities can either be output, intermediate, or input activities. Usually we work upstream from the final output activity that holds the finished product. Each intermediate activity will perform a transformation on the materials moving through it. In this process, we'll need an injection molding activity where the preformed reinforcement will be encapsulated in the over-injected polymer. And to produce the reinforcement panel, we'll need a preforming activity. The first activity in the process will be an input activity and will simply be a materials storage buffer to hold the materials coming into the process. Now that we have our activities defined, we can add them from the catalog to the process according to the desired process flow. As the activities appear, required input data will be highlighted with arrows. We start from the last activity at the top of the process flow diagram, since that activity holds the finished part and will include the value added by all upstream activities. We then add activities upstream until the process is complete. The next step is to add input data. For this process, we're going to look at making 10,000 parts per year. The process itself, we're going to assume is fully utilized. The part will include 2 kilograms of reinforcement material at 50 euros per kilo. The matrix content will be also 2 kilograms at 5 euros per kilo, and the over-injection polymer will be 6 kilos at 2 euros per kilogram. Next, we'll include the input data for the overmolding activity, a reject rate of 1 in every 1,000 parts, a cycle time of 3 minutes. There will be one operator, a tooling cost of 120,000 euros. Consumables per part will be 20 cents. The capex for the overmolding activity will be 800,000 euros. That equipment will require 50 kilowatts of power, and it'll take up 50 meters squared. There will be no scrap on the reinforcement and matrix. However, we will include a scrap rate on the injection molding polymer of 2%. Next, the reinforcement preforming activity. Again, we're going to include a reject rate of 1 in every 1,000. The cycle time we'll assume to be 4 minutes. Again, there'll be one operator, a tooling capital cost of 20,000 euros. The consumables used in this activity will be 5 cents per part, and the capex related to this activity will be 50,000 euros. That equipment will use 20 kilowatts worth of energy and will occupy 10 meters squared of factory space. The scrap rate on reinforcement and matrix we'll assume to be 30%. Lastly, we have the materials storage activity. Since this activity won't have a cycle time, we'll assume it to be 20% dedicated to the production of this part. We'll allocate half a person to the activity, and we'll assume the capex related to that activity is 20,000 euros. The equipment will use 10 kilowatts worth of power, and it will take up 20 meters squared of factory space. Now that the process is fully defined, you'll see that all the calculations have been solved. Scrolling up to the last activity in the process, we can see some of the final results. The process production cost is 42,77 euros, and the materials cost is 130 euros. But we need to add a product price and interest rate in order to calculate the return on investment for the part. Here we're going to use a price of 200 euros and an interest rate of 2%. Once we've filled in those numbers, the final calculations can be completed, and we have a result for return on investment for the part. There is, however, some input data that applies to all activities in the process. These attributes have the same value regardless of activity. Let's assume the cost rate for direct and indirect personnel is 25 euros per hour and 55 euros per hour respectively. We'll also assume that any tool in the process will last at least 100,000 shots. Now let's plot some of these results. To set up a new chart, we're going to close the attribute and the activity browsers and open the chart browser. We add a new chart, give it a name. In this case, we're going to look at a breakdown of the total cost by cost attribute. In this model, the cost attributes we want to plot all include the product cost process tag. So we can simply drag and drop this tag onto the chart to generate the desired pie chart. Now let's create a sensitivity analysis using an XY line chart. Here we're going to look at how the output affects the total part cost. To do this, we simply drag and drop the desired attributes onto the chart. We'll set a range from 5,000 to 50,000 parts per year in increments of 5,000 parts per year. In this case, the model has been designed to multiply activities in parallel in order to meet the desired output rate. The effect of this can be seen in discontinuities in the cost versus output sensitivity plot. To investigate this in more detail, we can look at each of the cost attributes separately for the specified output range. Simply drag and drop the cost attributes from the process flow diagram onto the chart. Here we have direct and indirect personnel, equipment, tooling, energy, maintenance, and facility costs. And finally, to finish the plot, one can set the number of decimal places displayed, the y-axis increment, and minimum. This video has shown you how to set up a new process from scratch. The next step is to use that model to create new variants and scenarios for optimizing the processes, pricing technology, and de-risking investments. If you want to know more, get in contact and we'll show you how InCA can provide you with the insight you need to make the right decisions.